In this video, we're going to discuss topics from Chapter 15. The textbook actually does a pretty good job of covering this material, so in this video I'm going to try something a little different. I want you to read through the book first, get all that background material, and then watch this video. So again, go read through all of Chapter 15 and then come back and watch this video. The reason why is because I'm not going to explain the material. I'm going to let the book do that. What we're going to do is I'll give you a little bit of explanation, and then we're going to spend most of the time just covering example problems. Lots of example problems, and if you don't have the background information, it might not do you all that much good. We're going to start with the issue of temperature. Temperature is a word that we use all the time, and everybody knows intuitively how to use it. But I'm curious how many people actually know what temperature means from a fundamental physics standpoint. Temperature is defined as a measure of average kinetic energy of atoms or molecules in a substance. This definitely is not how we use it in our day-to-day conversation. But from a fundamental physics standpoint, this is what it's representing. It's hard to demonstrate the fundamental meaning of temperature because we are unable to visualize atoms and molecules, so we can't see the kinetic energy that temperature is supposed to be representing. So I'll do my best with maybe a simple simulation like this. So in this simulation, these little particles are supposed to represent H2O, or water molecules, each one of these. So this is a collection of water, and it's in a liquid state right now. So if I push play here, you can see what I mean by temperature. See how each molecule is vibrating and shaking around. So that's a measure of the temperature. So if I add heat here, I warm them up. What you're seeing is they're starting to shake faster. They're getting a little more excited. They're moving around more. They're spinning more. Okay, this is what we mean by the average kinetic energy. So the higher the temperature, the more these things start really moving around. They crank this up more. See, some have actually broken off and escaping. So in terms of water, that would be representing evaporation, when individual molecules are actually gain enough energy to escape. Anyway, this gives you at least some sort of way to visualize temperature. A word that's often used with temperature is the word heat. For example, if you're cold in a room, you say turn up the heat. Or if something's really hot, we'll often say that there's a lot of heat. Unfortunately, those aren't at all the way we use that word in physics. You've seen that several times now, that a word is different than the way it's commonly used. So in physics, heat is energy transferred between objects of different temperatures. Maybe I can emphasize this with an example. So let's say we have two objects with the same temperature and they're in contact with each other. Is there any heat? With the way we use the word heat in everyday life, then we would maybe say yes, because we have hot objects, so doesn't hot mean lots of heat? Well, from the definition of heat, no, that's not how it works. So energy transferred between objects of different temperatures. If we have two objects with the same temperature, it doesn't matter how hot they are or how cold they are, there is no heat. There has to be a difference in temperature for energy to be transferred through heat. So you can see that we use it differently in physics than it's normally used. So let's address this question then. What does heat do? Well, it changes the internal energy of an object. I need to highlight here, internal energy is often referred to as thermal energy. These basically mean the same thing. Our book really likes the term internal energy, so I'll use that to stay consistent. But either one is pretty much well accepted. So there's a mathematical definition of heat. Right, heat usually is given the symbol Q. Mathematically, it's equal to the mass of the object multiplied by this thing right here that I'll mention in a minute. And then this is the change in temperature that the object underwent. The whole point of heat is to add or remove energy, transfer energy. That results in a change in temperature. This C here that I mentioned, that is known as the specific heat capacity. What that represents is the amount of heat energy required to change the temperature of a unit of mass by 1 degrees Celsius. We can take this equation up here and rearrange it to maybe understand what specific heat capacity does a little bit better. Now in this class I mentioned at the start of the semester that I'm not going to use a lot of math, and this one certainly would require a bit of math. So I'll do my best to explain it from a conceptual standpoint without plugging in a lot of numbers into equations. Mathematically, though, we can't ignore that when we write the heat equation above in this form, we can see that the specific heat capacity is in the denominator, which means then that if you have a larger specific heat capacity, the change in temperature will go down for a given amount of heat. Or maybe we can say it this way. If the specific heat, the C here, is larger, it requires more heat energy to change the temperature of an object. If it's not making sense with those definitions, maybe let's go through some examples. Here's some specific heat capacities for some common materials. If you compare aluminum at 900 and let's say, I don't know, lead down here at 128, what does that actually mean? If you had 1 kilogram of aluminum and 1 kilogram of lead, it would take 900 joules of energy to increase the temperature of the aluminum by 1 degree Celsius. That's what the 900 means. In comparison, lead would only require 128 joules to do the same. So that would be the increase of 1 degree Celsius. So the specific heat gives you an idea of how much energy you need to add to change the temperature of an object by a certain amount. Okay, so bigger specific heat capacity means more energy is required to change temperature, or if you want to think of it as to lower temperature, more energy is required to be removed. You have to lose more energy before your temperature drops. So one way we could interpret this is because aluminum is much higher, we could say that aluminum is better at storing thermal energy. So when you add energy to it, it does a lot more with that. There's little reaction from aluminum for a given amount of energy that's added or taken away from it. Okay, well, that was aluminum at 900. Notice water in its liquid state is 4,190. So it's more than 4 times aluminum. What that means is water is really good at storing thermal energy. You have to add a lot of energy to water to get it to change its temperature by 1 degree. Or you could think of it the other way around. You have to take a lot of energy away from water to get it to change its temperature by 1 degree. So what we can say then is water is one of the best at storing thermal energy, and that turns out to be true compared to all common substances. Water has an abnormally high specific heat capacity. From my own experience, I found that if all of this still isn't quite clear, going through several examples helps clear that up. I mentioned at the start that we're going to do several example problems, so that's when we're going to get into those is right now. Here's our first one. I should mention that I'll go ahead and let you read these rather than me read them to you, and then I'll discuss the answer with you. So on this one, if you're ready, the answer is C, specific heat capacity. Okay, so thermal inertia, I underline this word here. Inertia, if you remember, that represents a resistance to change. So thermal inertia is a resistance to change in thermal values, or you can think of it as temperature. So specific heat capacity is that energy storage, or in other words, the amount of energy you need to change temperature. So if you are resistant or reluctant to, if you're a substance that's reluctant to change its temperature, it must have a high specific heat capacity, meaning it requires a lot of energy before it's willing to change that temperature. If it helps, I'm trying to personalize some of these traits. Let's try some more. Okay, this one is actually all of the above. Okay, so yes, it does relate to specific heat capacity, but it goes back to this equation that I gave earlier, where the heat or the energy transferred is equal to the mass of the object multiplied by its specific heat, so it's energy storage, multiplied by the actual change in temperature. So all three of those quantities define the amount of heat that was involved. Next one. Okay, the answer here is iron. This is one that a lot of students miss at first, because you're used to thinking, okay, a high value means it should happen faster, right? And it doesn't work that way for specific heat capacity. So the higher the specific heat, the more energy you need to change any of the temperature. Iron has a small specific heat, meaning a little bit of energy will change its temperature a lot more than aluminum would. Let's try another one. Okay, the answer would be a low specific heat capacity. Remember, low specific heat means that it has to lose very little energy to change its temperature. So because it has to lose less total temperature, it's probably going to happen faster. Where a high specific heat capacity means more energy is required for the same amount of temperature change, so more than likely it's going to last longer because it has to lose more overall. Again, this would be low specific heat capacity. If it's very hot in the day and then very cold at night, that means its temperature is fluctuating a lot. It's increasing to a high value and then it's dropping to a very low value. So it's not retaining the heat very well. It's not holding on to it. It's it's absorbing it and then releasing it relatively easy, which means probably not a lot of energy was required to change its temperature in the first place. Try this one. Okay, well, if you've ever just tried to boil a pot of water for spaghetti or something like that, you know that it actually takes a while to get that boiling. And the bigger the pot, the more time it takes. So the answer in this case is a long time in changing temperature. Remember, water has one of the highest specific heats of any common substance. That means it requires a lot of energy every time it changes its temperature by 1 degree. So that's why it takes so long, is because you have to dump a lot more energy, so it just takes more time to distribute all that energy. Okay, well, this is kind of using that same idea just in reverse. If it takes a long time to heat it up, then it should also take a long time to cool it off because it's got a lot of energy stored. So to cool off 1 degree, it's got to get rid of a lot more energy than other substances. So if its specific heat were lowered, that would mean it would take less energy to change its temperature. So it should have a shorter, you should have a shorter bath if you had lower heat capacity. So there's a lot of reasons why it's good that water has a high specific heat capacity, and one of them is simply taking a bath. All right, try this one. So this is kind of the opposite of the previous question. I asked if the specific heat of water were higher. If it's higher, that means it requires even more energy to change temperature than it already does. So it's going to be able to store even more energy for a given amount of temperature change. So that would mean it's less likely to freeze because it has to lose a lot more energy before it reaches the freezing point of 0 degrees Celsius. All right, here's one more. This one's might be a little trickier, so try it out and see how you do. Well, if you've ever just bitten into a really hot piece of pizza, you know that it's the sauce that burns you, not the dough. If the sauce has a higher heat capacity, that means it's storing more energy, so there's more available there to dump into your lip or your tongue when you bite into it. Now, I said this is a little tricky because it also depends on something that we'll talk about in chapter 16, which is conduction, so the rate at which energy is transferred. Turns out that tomato sauce not only stores more energy, but it also transfers energy faster. So the combination of those is why you'll get burned if you try to bite into a piece that's too hot. But it's not the dough that really does that, it's the cheese or the sauce. Let's take a little break here. In our next video, we'll continue with the concept of thermal expansion.